So in this example, we're asked to draw our shear diagram and our moment diagram for the beam below. Okay, so this beam has a pin joint at point A and a roller joint at point B. Alright, so at point B, we'll apply a force normal to the point of contact, NB, and at point A, because it's a pin joint, we'll say we'll have two reaction forces, AX and AY. Okay, so the first thing we're going to do is we're going to solve for A of X, A of Y, and NB. Okay, so I think the easiest one to do right away is we'll sum all of our forces in the X direction, and so that equal to 0. In that case, our only force in the X direction is AX, therefore A of X must be equal to 0. Alright. So our next one we're going to do is we're going to sum our moments about point B and set that equal to 0. Alright, so if we do that, we'll get minus A of Y times the length of the beam, which is 9 meters. Alright, and then we have to account for the force, the concentrated force within the distributed load. Alright, so this distributed load, I'll highlight it in green here. This distributed load. Here, we can simplify it down to being a single concentrated force. Alright, and that concentrated force will be applied at the centroid of the triangle. So if you go back to lecture 10, alright, there's a nice table in lecture 10 that will say for a triangle we know that our concentrated force will be equal to the area under the curve. Alright, so the area under the curve here is going to be equal to 1/2 the base times the height. So our base is 9 meters long, and then the height of our triangle is 6 kilonewtons per meter. Alright, so that's 54 divided by 2, or 27 kilonewtons. And that's going to be our concentrated force. Alright, and then X of C, we know is going to be the centroid of our triangle, and then for a triangle, we know that X of C is going to be equal to 1/3 of the base. Alright, in this case it's going to be 1/3 of 9 meters, which is going to be equal to 3 meters. Alright, so using F of C and X of C, we can determine the moment due to that distributed load at point B. So we would say that's going to be equal to a positive 27 kilonewtons times 3 meters. Alright, and then N of B goes through it, so there would be no other moment. So if you solve for A of Y, alright, we add A of Y to the other side and divide by 9 meters, we get 27 kilonewtons times 3 meters divided by 9 meters. Alright, so that would be equal to 9 kilonewtons. Alright, and then we could sum, to find our last force, we can sum our forces in the y direction and set that equal to 0. If we did that, we would get 9 kilonewtons minus 27 kilonewtons plus NB. So if we solve for NB, we would get NB would be equal to 27 kilonewtons minus 9 kilonewtons, or 18 kilonewtons. Alright, so that's our first step. first step, we found all of our 3 reaction forces. All right. So the next step we're going to have is we're going to draw our section cut. All right. So our section cut here. So we're going to draw it. I'll just draw it anywhere in the beam. I'll call it section cut A, lowercase a, lowercase a. All right. If we do that, we'll end up getting A of y, which was equal to 9 kilonewtons. Right. We still have our distributed load. Alright. And I'm going to say, you can see that W of x is equal to 2/3 kilonewton per meter squared x. All right, and then we have our at our section cut AA. We will have our 2 internal forces. We'll have V of A, or is it V of x, and we'll have our moment M of x. All right, so so how I was able to determine this function here is we know that at W of x, when x is equal to 0, we know that W of x is equal to 0, and then at x is equal to 9 meters, we know that W of x is equal to 6 kilonewton meters. Alright, so what we can do is we can use, to determine the slope, alright, is we can subtract our 2 x values. So our x values are 9 meters minus 0 meters. Alright, and then our y values were 6 kilonewton meters minus whatchamacallit here, minus 0 kilonewton meters. Alright, and then that would give us our slope of our line here, which would be equal to 6/9, or 2/3. Alright, so that's where the 2/3 comes in over here. Alright, so and these should be kilonewtons per meter, not kilonewton meters. Sorry. Here. Alright. Alright, so after that, what we can do is we're just going to sum all of our forces in the y direction to solve for V of x. So if we do that, we'll get 9 kilonewtons minus 1/2 W of x times times x plus or minus V of x. Alright, so what we'll end up getting is V of x is going to be equal to 9 kilonewtons minus 1/2 times 2/3 kilonewtons per meter squared times x squared, or 9 kilonewtons minus 1/3 kilonewtons per meter squared times x squared. Alright. Alright, and then the last one would be to sum our moments about the section cut and set that equal to 0. If we do that, what we'll end up getting is we'll get A of y minus A of y times x minus 1/2 W of x times x, which is our force, times our moment arm, which is going to be equal to x over 3. Alright, and that would actually be a positive moment. And then we'd get, this is our force, this is our distance. Alright, and then the last thing we'd have is we'd have our moment about x. Alright, so we can solve for the moment about x. That's going to be equal to a of yx minus 1/2 w of x times x over 3, which would be equal to a of yx minus 1/9 times x cubed kilonewtons per meter squared. Alright, so we can plug in now. We know a of y is equal to 9 kilonewtons, so we can plug that in. So this should be Alright, so now we have all of our two functions. So the last thing we'll have to do would just be to plot them. Alright, so if we plot these two, what we end up getting is v of x will start off at 9 kilonewtons. Alright, and then it's going to go down until we reach point B. Alright, and then at point B it should be at minus 18 kilonewtons. And then it'll go up back to 0 due to the reaction force NB. Alright, and then for m of x, alright, and this line is just our v of x function. Alright, then m of x is going to start off at 0. Alright, and then we know that that it's going to look like a cubic parabola or a cubic function. Alright, and we know that at x is equal to 0, m of x is 0, and then we know at x is equal to 9 meters, m of x is going to be equal to 9 kilonewtons times 9 meters minus 1/9 times 9 meters squared times kilonewtons per meter squared. Sorry, this should be 9 meters cubed, and then so we end up getting 81 kilonewton meters minus 81 kilonewton meters, or 0 kilonewton meters. Alright. So the one thing I'll point out here in this example is that we have we can determine when v of x is equal to 0, the moment is at its maximum value. So if you want to determine what is the maximum moment, you can solve for when v of x is equal to 0. So if we do that, we would get v of x is equal to 0 would be equal to 9 kilonewtons minus 1/3 kilonewtons per meter squared times x squared. So we would get x squared would be equal to 27 kilonewtons, 27 meters squared. Alright, so x would just be equal, v of x would be equal to 0 at x is equal to the square root of 27, which is about 5.196 meters. So you could plug in x is equal to 5.196 meters to determine the maximum moment would occur at m is of square root of 27 meters. Alright, so this is at x is equal to square root of 27 meters, and this is at x is equal to square root of 27 meters. Alright, so that so just to summarize what we did here, we first found our reaction forces, AX, AY, and NB. Then we took our section cut at within our along the beam. So we just picked any point, arbitrary point X along the beam. Since we had the same loading across the whole beam, we only needed to make one section cut. And then we summed our forces about Y instead of equal to 0 to find our V of X function. And then we summed the moments about X in order to determine our took moments about our section cut to determine our moment as a function of X. And then using those two functions, we were able to draw our shear and moment diagrams. Right, so that concludes our problem, this problem, and that concludes this lecture.